All right, so today it's day 57. Let's solve. We're gonna continue with lead code. We're gonna solve this one. I already saw the solution in the morning, and it was pretty complicated. I just remember the intuition. I didn't actually write the code. So with this one, we are gonna finish the first three data structures, and we're gonna be at 20 out of 150. So let's try to solve it. So the intuition for this one was essentially, I can say, okay, first the context of the problem. So you're given like a histogram, right? Which is gonna be like the left side, in which we're gonna have like some height of each bar, and we want to know what is gonna be like the biggest rectangle that can be formed in the with a histogram. And for example, for this histogram, the biggest rectangle has this area of 10, because you can like combine these two bar plots at this height. And that's it. That's like the idea. So for me, a good way to have like the intuition of the solution is first ask ourselves, what is the way in which we can solve it by brute force? So we would compute like every possible rectangle and then keep the max area. So one way of doing it is like, so a rectangle could be this one, right? Then this one, 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 and so on, right? So we would see this and we would say like, there's no sense of computing. I don't know, like if you know that the height is 5, there is no sense of computing like the rectangle of size like 1, then 2, then 3, right? And you would say like the smallest rectangle in 1D is gonna be, at least it's gonna have the height, the maximum height, right? So you can like per-filter it. And you can apply this logic not only in the height in 1D but in 2D. So you can say like, instead of computing, okay, maybe I should explain, because this problem is actually quite hard. Maybe I should explain it like this with the image. Just to show the intuition. So what I'm saying is like the first approach is to compute every possible rectangle, which is gonna be like, you can compute this rectangle, then this rectangle, then this rectangle, then this rectangle, then this, and so on. There are so many. So what I'm saying is like, I mean, you just compute, if you had like only one bar, the biggest rectangle is just gonna take the maximum height, right? So there is no need of computing every possible one. Okay, and this concept applies also like in 2D. So instead of computing, for example, I'm gonna put this example, we can compute this rectangle, right? This is a rectangle. And then we could compute, I don't know, like this rectangle, and then this rectangle, and then this rectangle, and then these rectangles, which doesn't make sense, right? So we can say like, you know what? It's gonna be capped by like all these smaller rectangles are gonna be like dominated by the bigger rectangle, which is like this one. I don't know if it makes sense. So you can think about it like the intuition, the solution is like, the only thing that you want to search is the rectangles for which exploit the maximum height and are bounded like by some walls, right? And I'm gonna show what are like these rectangles, which essentially is gonna be like, I don't know, for in the second position, this is it. For the first one, it's gonna be this one. For the fifth one, it's gonna be this rectangle. For the 6, it's gonna be this. For the 2, it's gonna be this, and for the 3, it's gonna be this. So what we are essentially saying is that we're gonna, for a given height of a bar, we're gonna check how much can we extend like this area over the left and over the right. So if we are at 5, we check if there is a height that is smaller, and this height is gonna serve like as a wall, right? And we're gonna check to the left and we're gonna check to the right. And in this case, when you arrive to 2, there is like a wall. So this is gonna be like the maximum area you can achieve with the height 5. And you do this for every height. So for the height 2, the maximum area is going to be just this rectangle, right? I mean, for this bar, but for this bar is going to be this rectangle. No, it's going to be actually this rectangle, right? And so on and so on. So one way of doing it is like checking all possible combinations, which is going to be like O of n squared, because for everyone you're going to iterate over all the other and check if you can extend like the height. But we can do it better with the stack, and then intuition is like you gotta have a strictly increasing stack. So it's gonna be, you iterate over each element, over each bar in the histogram, compute the area, right? If it's smaller, okay, so you add it to the stack. If it's smaller, you're gonna evaluate the areas in the stack. If it's bigger, you're gonna add it to the stack. So first the stack is gonna be like empty, right? Then we arrive at the first position and we are gonna add the 2 to the stack. Okay, then we're gonna go to the second position and find that the value in the second position is smaller than the last value in the stack. So it means that we already find like we find already like area, like the walls of the maximum height 2, you know, for this bar. And then yeah, like this is gonna be the area, and then you append this value to the stack. So now the stack is gonna have a 1, and then 5 is greater than 1, so you add 5, right? And then 6, so you add 6, and then you're at 2, and you say like, you know what, 2 is smaller than 6, so now we have to pop 6. And now yeah, and then we compute like the area. Basically we have to compute the left wall and the right wall. For the right wall is like literally the current index, which is gonna be like I, and for the left wall, I mean, it's gonna be the previous, after you do a stack, it's gonna be the last element in the stack. So it's gonna be like a stack minus 1, right? Which is gonna be like this one, this position. So this is gonna be the area. So with both indices, you compute the width, right? And then you can compute the area. And while the value in the stack is bigger, right, than the current value, you're gonna repeat, right? So you're gonna now be at here, compute the left wall and the right wall. The left wall is gonna be here, the right wall is gonna be this one. With this you can compute this width, and then you multiply it by the height, and you're gonna have this area, and you just like save until this step, like the max area, and so on. So now at the next iteration, these values are gonna be out of the stack, and it's gonna be only this value and this value. And now we can go like to this iteration, and we add it to the stack, right? And then it's finished. So some trick that it's done is to add like a 0 to the stack. And you add a 0 at the end because you are forcing to create or also like these rectangles, because otherwise you would not compute them. But that's basically the main intuition. I think it's a bit complicated to understand, but I guess it's pretty clear once you understand like the use of stack always in this type of lead code problems. And the main understanding is just there is a way in which you can always add values to the stack in some sort of order, and you could always solve the problem by some sort of combination, but using the stack means that you can update, like delay the update of some values and put them in the stack to be updated later. That's like the main intuition. You're gonna use a stack for which, because you don't want to check like values many times, you want to do it only once, and you don't want to do it, and you can delay like this, and you can come back to update the values. That's like the intuition. All right, so let's do it. Let's do it locally. So let's take the heights. We have to return the area, the actual biggest area. All right. So this one I have not done it. I know the intuition how to solve it, but I have not tried it. So let's try to do it. The solution is gonna be, basically we are gonna iterate. Okay, first we gotta start with an empty stack. I'm gonna change the name, like think that the representative name to be updated or to be computed in this case. Here I'm gonna add that essentially, so for a given height of each var, we are gonna delay the computation of the max rectangle with the given area, with the given height at the given bar plot. Okay, I think it's too much explanation. Okay, next one, it's we're gonna iterate over heights for height in heights. Okay, so first what we do is we're gonna have like some while loop. Like, I don't know, I'm just gonna skip the logic here. And because the first iteration, the stack is gonna be empty. So if it's not empty, we're gonna check like some sort of condition. And the condition, as I said, is if the next value that we are iterating over, this one should be smaller than the one in the stack. Or you can say that the one in the stack it's bigger than the current value. Okay, and we have to have the current value. And I think that we're gonna work with indices. So let's use indices instead. So the current value is gonna be heights I. So the value, the index, which is gonna be height of the stack okay, so what I'm saying here is that the index here is the index of the last element in the stack. What I'm saying is the height of the last element, it's greater than the height of the current element. So while this is true, we're gonna we gotta pop this element, right? So we're gonna compute the area of the element. So in order to compute the area, we're gonna determine the height. So let's say that the height it's gonna be equal to let's see just the iteration. So this is gonna be 0, 1, 2, 3. This is gonna be in the stack, but when we reach 4, it's when we're gonna compute the previous one, right? Yeah. So here it's 0, 1, 2, 3, 4. So at the iteration 4, the height it's gonna be this one. I mean, it's gonna be pop. I think we can do pop directly. So we can do this one. And instead of putting -1, we're gonna put dot pop, right? And this is our height, right? The 6. And we want to say we now have to compute the left and the right barrier. So the left barrier, let's call it first. Let's start. I mean, the right, it's gonna be just I, the current index. So I don't need to put it. And the left, it's gonna be I mean, it depends. Because, let's think about it. If I do pop of this, the left barrier is going to be this one. have to do it. No, but then I will have like 2 while loops. No, I think only one. Let me think about it. Because if I have I, the left is gonna be the one in the stack, like the index of the last one in the stack. But it's while the stack is empty. Yeah, so in the first iteration is gonna be this one. In the next iteration is gonna check this one. You're gonna do pop, and the left barrier is gonna be this one. Okay, no, it makes sense. Alright, so this is the left, and then the width, it's gonna be the current minus the left. Okay, I'm gonna put the right, just to be more explicit. Right minus left. So let's just check the indices, if they make sense. So, for example, if I'm at 5, if right should be 0, 1, 2, 3, 4, which we know it's going to be 4, and left is going to be 1, right? So 4 minus 1 is 3, but this should be 2, so it's going to be right minus left minus 1. And then the area, it's going to be height times width. And then we're gonna say that the max area is gonna be 0, and we're gonna say that the max area is gonna be the maximum between the it's gonna be like a global max area and area. And once we finish this, we're gonna append the current height. So we have to say to be computed dot append I, and in the end we gotta return the max area. Let's run list index out of range. Okay, there are 2 things that I didn't consider, but it's okay. The first thing is like we're not adding the 0 at the end, that's one thing. And the second is this error. How to solve it? It says while to be computed and heights to be computed, this is an index, these are the heights, and this is greater than cur, which is okay. And then the heights of the lax is index in the stack, and you'll pop at the same time. So if you have 6 and 2, you're going to have the index 3 and 4, and you say cur, which is going to be the index I, which is going to be 4, so you have height 4, which is 2, and then you have to be computed minus 1, and you append 3, so the last index is 3, and height 3 is 6, and 6 is greater than 2, okay. So now you pop that value, so the height is 6, and then the left side you check this one, the 5, but to be computed, I mean, it has a value, 1. Okay, I'm gonna print it maybe here to see what is happening. So we add the index 0. Okay, it's even making a mistake from, so I add the index 0, then we have the index 1, and then we're saying while to be computed, which is true, right? So we pop the value 2, now the stack is empty, and this is to be computed minus 1 if the stack else -1. Yeah, because if it's the stack is empty, it means that it's the first element, and if it's the first element, it's gonna be one below, because for some reason Python starts at 0, so one before 0 is -1. So now it works. Good. Now there is one thing we gotta check, which is that at the end we gotta append the 0. So period.append 0. Does this simply solve the problem? Let me think about it. We are 3, but at I3 the stack is also gonna have 0. Okay, I think one way of solving it, it's like doing the iteration to length of heights plus 1, and when I is equal to length of heights, so basically current heights I is gonna be this if, okay, I think one cleaner way of doing it is say it's gonna be 0 if length of heights, else it's gonna be heights I. So I think this is cleaner. Okay. If I equals length heights. Okay, now it's working. I mean, let's try. Now that I solved it, I realized that it was not hard. But to be honest, it took me a lot of time to even understand the solution. Let's submit. Okay, good. Alright, that's it for today. Only one problem.